So yesterday we stopped. We did problem number 6. We did half of the problem. We created the table. Okay. So the table. So the game is this: you roll a die. You roll one die, one six-sided die. If you get a 6, you get $100. If you don't get a 6, you roll again. And if you get a 6 on the second one, you win $50. If you roll anything else, you get 0. Okay. So there was 3 things that could happen. Win $100. Well, how do you win $100? You roll a 6 on the first one, right? So the probability of that is 1/6, which if you change to a decimal is 0.166666 forever and ever and ever. Okay. How do I win $50? Well, to win $50, 2 things have to happen. I have to lose the first time. That's 5 out of 6. And then I have to win the second time, right? So the way down that path is here and here. So 5 6 times 1 6 is 536. Okay. And then the last way is to lose everything, not win a dollar, not win any money. Well, you don't roll a 6 and you don't roll a 6. 5 6 times 5 6 is 2536. We stop right there. Okay. So now we have to find the expected count, expected value. How much do I expect to win if I play this game? Okay. How much do I expect? Not how much can I win? I know I can win $100. I know I can win $50. I know I can win nothing, but how much would I expect? Okay, that's the mean. So to do the mean, we multiply the number, the random variable, times the probability. There's only 3 of them, so it's not very long. And then the second random variable times the probability plus the third one, which is $0.2536. Anything times 0 is just going to be 0. So the last one is just going to cancel out. So really it comes down to the middle 2. Okay. So if you multiply 100 times 1 6 is going to be 16.67 or 667. 16.667. And then 50 times 536 is going to be 6.94444444 forever. Add those together, and you get $23.61. Okay, that's the expected value. Okay. Here's a question I'll ask. When is it worth my while to play this game? When is it worth my while to play this game? That's a question I would ask on a test. I would say part A would be make the table. Part B would be give me the expected value. Part C would be when is this game, when should I play this game and when should I not play this game?
You have to spend less than 23.61 to play.
There you go. Anything, so to play the game, if you only have to pay $1 to play the game, it's worth my time. It absolutely is worth my time because I expect in the long run, right? In the long run, I would expect to average about $23.61 every time I play. In the long run. If it's $1, then yeah, the odds are in my favor, right? But what if they say no, it's $50 to play? Then it's not, right? Then on average, I'm going to lose $26.39, right? If they say well, it's $20 to play, $20 to play this game. In the long run, yes, right? Maybe not once or twice, but if you're going to play this game over a long period of time, then yeah, maybe $20 a turn. would be because you're up $3, right? You're going to be up $3 in the long run. So that's the type of question. Anything above the expected value. So anything above the expected value they want me to pay, it's not worth it. I'm going to end up losing money. And that's how casinos make their money. They know this. They know this number. If you play this game, they know what the expected value is going to be. They've already done the math. So they say, you know what? We're going to make it worth this much money. We're going to make this game, you have to pay $30 every time you play this game. Are there going to be winners? Yeah. But for every, in the long run, they're going to make $7, $6 every time if they make $30, right? That's what they know. So before they decide how much a game costs, they do this math. Okay, they know the expected value. And then the next thing they would do is probably standard deviation. How much would that number vary? Would it vary by a lot? Would it vary by a little? That's the other thing they would want to do too. Okay, so yeah. So like I said, that game would be worth my while if I paid less than $23.61 to play in the long run. Anything more than that, not worth it, because the odds are not in my favor anymore. Okay. Okay, so here we go. Here's a variation. Number 7 is a variation of the same game. Variation of the same game. So what I want you to do for A, B, and C is find me two things. Give me the mean and the standard deviation. Expected value and standard deviation. If I doubled the amounts of winning. So now it's no longer 100, 50, and 0. If I double the amounts, it would be 200, 100, and 0. Okay.
The same probability applies.
Probabilities still apply. Yeah. Same game. Same game. Part B says you play the same game twice without doubling. So without doubling, you play twice. Part C says original game, you play 200 times. Okay. Give me the mean and the standard deviation for A, B, and C. So each A, B, and C, you're going to have two answers. Mean, standard deviation for each. Okay. So that's what I want you to do. Okay. I'll give you guys 5-10 minutes, and then we'll go over it. Okay. So let's look at this. If you're not done, that's fine. We'll go over it together. We'll start going over it. Okay, so the first one is we double the dollar amounts. That's the X. X is the dollar amounts. So 200, 150, 0. Same probabilities. I'm not changing any of the probabilities. It's still the same game. Okay? So I'm just doubling everything. I'm doubling X. Well, that's just that. You're multiplying something times X. You're doubling X, 2X. And the standard deviation, you would do the exact same thing. So take the original and multiply it by 2. Okay, so let me go back to the problem. So the original expected value was $23.61. So you would say 2 times that. And you would get $47.22. Okay. Standard deviation, you would do the same thing. 2 times, so we don't have that number, do we? So we have to use our calculator. We got to use our calculator to find it. Okay. So we're going to put this table in L1 and L2. Let me do it up here. Let me do it on my computer one, so you guys can. So we're going to put that top table in L1 and L2. 150, 0, 16, 536, 2536. Okay? And then we're going to find the standard deviation. Okay, so once it loads up, oops, wrong one. Okay, so I'm going to delete or clear my other tables. Oh no, sorry, I'm not going to put 150 and 0 because it's doubling, right? So I'm actually going to put 200. No, wait, no, because I want to find the original. Okay, yeah. Forget what I just said. Okay. Probability of 100 was 1 divided by 6, so 1 divided by 6. It changes it to a decimal for you. 5 divided by 36. 25 divided by 36. Okay. Now I go to stat. Anytime you want to find a standard deviation or a mean, you always go to one-var stats. L1 is your list. Those are my random variables. Frequency list means the probabilities. Okay. We already know the top one, the mean. $23.61. We got that one already. We just need the standard deviation. The standard deviation for this guy is $38.16. That's what we're going to double. We're going to double $38.16. And we get $76.32. Okay. That's the mean and standard deviation if I were to play with higher stakes. 200, 100, nothing. Okay. The next question says, now you're just playing the game twice. Regular stakes, so regular 100, 50, 0. Regular stakes, nothing's changed. This table here, I'm playing twice. Well, that's this guy right here. This guy right here. So I would take the expected value of my first time plus my expected value of my second time. Well, it's the same game, you're playing twice, so the expected value is going to be the same both times. So it would be $23.61 plus $23.61, which is $47.22. That's how much I would expect to win if I play twice. Okay. Standard deviation, though, that one's got a different formula. That one's got a different formula. That formula is right here. You take the first standard deviation, square it. You take the second standard deviation, square it. Add them together, square root. So the first standard deviation was $38.16 squared plus $38.16 squared. And then find the square root. $38.16 squared plus the same number, square root, and I get $53.97. So the means are the same. I would expect to win the same amount, but the standard deviations are different. Why are the standard deviations different? It's the same thing, right? Doubling the stakes and playing twice, right? Double or nothing, right? That's all it is. That's what it means. Double or nothing. Why are they? Exactly. So what happens the more you play? The more you play, what happens to the variability? Decreases. The more you do anything, the less the variability is going to be, the less the spread, right? As I play more and 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 more, standard deviation will always go down. The first one I only played once. And once anything could happen, right? You walk into a casino, you put money down, anything could happen. You don't know. But the more you play, the more you know what's going to happen. You're going to lose. Okay? Okay, so last one. Last one is just like part B. Part C is just like part B. The only difference is now you're going to play 200 times. You're going to play 200 times. Well, I don't want to have to add the same number 200 times. So what's a quicker way of doing expected value instead of having to add the same number 200 times? There you go, right? Instead of going 23.61, 23.61, 23.61, 23 points, because that's what I'm doing every time, right? Because I'm paying 200 times. Instead of doing that, multiplication is the faster way of doing addition. We get $4,722. That's how much I would expect to win if I were to sit there and play this game 200 times. Back to back to back to back. Regular stakes. I'm not raising the stakes. Okay, now standard deviation. Well, it's the same formula I use for B. Again, I don't want to have to write. So it's 38.16 squared plus 38.16 squared plus dot 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 plus 38.16 squared. You do that 200 times. Well, again, what's a faster way of doing it? There you go. Do it once. Figure out what 38.16 squared is, and then multiply it by 200. So 38.16 squared times 200. So I get the square root of 29. Actually, I'm not going to write down that number yet. I don't want to round to the end. So let me find the square root of it. Up. Okay.
We multiplied 30.16 squared and then multiply by 200.
Yeah, because it's the same number 200 times, right? Because you're just doing that 200 times. So instead of adding all 200, let's just do it quick. Multiply by 200. Take the square root. Okay. All right, last one. Last one. This question was a free response question that used to be on tests. I put it on tests for like 3 or 4 or 5 years, but then I liked it so much I took it off the test because it's a good problem. Because I've seen problems like this on AP and on tests in this class. So that's why I put it in the notes, because it's a really, really good problem. Okay? Bicycle store problem. So bicycles arrive at a bicycle shop in boxes. So if you go to a bicycle store, there's not too many bicycle stores now, but there used to be bicycle stores. Like you see Stevens Bicycles, I think is one of them, something else. They don't build the bicycles. They get the parts from somebody, usually overseas. They put them together. They put the bikes together, and then they sell them, right? So when they come in from overseas, wherever the factory is, they put them up. They set them up. So there's 3 parts to it. 3 parts before they can give them to the customers. First thing is unpacking. They have to take everything out of the boxes. Second thing is assembly. They have to put them together. Third thing is tuning it to make sure it works right. Okay, there's 3 parts to that, and then they can give it to a customer. Before they can't give it to a customer unless they do that. So what happened here is the owner or whoever took the average time. How long does it, on average, does it take my workers to unpack, to get them all out of the box, to get a bike all out of the box? About 4.5 minutes. Number varies by about 0.7. Okay, once they have it out of the box, on average, how fast is it? How fast can they get it put together? About 21.8 minutes. Varies by 2.4 minutes. And then how fast can they tune it afterwards? 12.3 minutes. That number varies by 4.7. Okay, so my question, before we get to the question, if I walked into the store and I wanted them to take it out of the box, put it together, tune it, how long would I expect to be waiting? On average, how much do I expect to wait? How'd you get that? There you go. You just add up all the average times, right? There's 3 stages. You add up the average time. So I would expect to be waiting 30, what'd you say, Jordan? 38 minutes and 0.6. 38.6, yeah, 38.6. A little over 38.5 minutes. Okay? So it says here, based on these past experiences, the manager makes the following assumptions. The times for 3 setups are independent. The times for each phase are approximately normally distributed. So right here, this guy right here should be a good key on what we're going to do. Normally distributed. There's a reason why they put normally distributed. 99.9% of the time they put the term normally distributed in there, we're going to use normal distribution. The curve, shading, all that good stuff. Okay? Okay. So here's the question. A customer decides to buy a bike like the one the display models want, like one of the display models, but he wants a different color. He or she wants a different color. The shop has one. It's still in the box. Hasn't been put together. Hasn't been unpacked. It hasn't been assembled. It hasn't been tuned. The manager says they can have it ready in half an hour. What's the probability that that actually happens? So I'll give you a hint. We're going to use normal distribution. So anytime we use normal distribution, what's the first thing we got to do? Draw the curve. Yep. Draw the curve. If you're ever stuck and it says normal distribution, draw a curve. Put the mean in the middle. The mean always goes in the middle. What's the mean? There you go. Isn't that the expected? Expected is the mean, right? 38.6. Good. 38.6 is going to be the mean. That's the expected time for them to go from beginning to end. What's the question asked? Of what happening?
Getting it done in less than how many?
Okay, so how much is half an hour? 30 minutes, so that's going to be over here. Which way am I going to shade, left or right? There you go. Anywhere in here, they fulfilled their promise. Anywhere in here, they fulfilled their promise. Anywhere outside of there, they haven't fulfilled their promise. It's greater than 30. Okay? So if I want to find that area, that's the probability. what do I got to do next? There you go. Let's do z-scores. X, which is 30, minus the mean over the standard deviation. What number do I put for standard deviation? So I could add them all up like I did like I did the mean, right? That's not what I'm going to do. Why not? Yes. Right? Yep. Just like this right here. Right? We added all of the 3 expected, but we can't do that with standard deviation. We have to do the first one, square it, second one, square it, third one, square it, and do it that way. That's how we have to find the standard deviation. So the standard deviation is going to be 0.7 squared plus 2.4 squared plus 4.7 squared square root. And then square root. 5.324. Okay. That's the number that's going to go down here. I wouldn't round until we get to the z-score. Yeah. Try not to round. Always try to go 3 spaces until the very end. Because just to try to be as consistent as possible. Okay? So we get 30 minus 38.6. Divide that by 5.324. Negative 1.62. Okay. Go to your tables. It is right there. 0.0526. 0.0526. Now, my question is that the shaded or is that the non-shaded? That is the shaded. Last thing is we have to explain it. There is a 0.0526 probability of getting the bike ready or getting the bike set up within 30 minutes or fulfilling the promise. You could say or fulfilling the promise because that's the same thing. There is a 0.0526 probability of getting the bike set up within 30 minutes or 0.0526 probability of fulfilling the promise. Either one. What is the probability that the tuning stage takes longer than the assembly stage? The tuning stage takes longer than the assembly stage. So the tuning stage. How long does the tuning stage usually take? Okay, how long does the assembly usually take? So on average, how much more, which one takes longer? By how much? Okay. So assembly minus tuning usually takes 9, just 9 whole? 0.4 minutes longer, right? So on average, I would expect assembly to take 9.5 minutes longer than tuning. That's the expected value, right? What's the standard deviation of those guys going to be? Say it again? So what's the standard deviation of assembly minus tuning going to be? I can subtract the means just like you did, right? But I can't subtract the standard deviations. I have to add them and square root them. Okay, so assembly usually takes 2.4 and tuning takes 4.7. So I get 5.277. Okay. So normal probability. They're asking me probability, so it's normal. What's the mean going to be? What's the mean going to be? 9.5. Good. That's the expected value, right? 9.5. How do I decide where to shade? I got it. This is going to be determined by the question. Well, which number is it going to be? It is a number line, right? Where is my? It's going to be over here. Is it going to be over here? Where is my dividing line going to be? Well, what is the question asking? So when is tuning going to be longer than assembly? Not after 9.5. What has to happen? Think of this guy here. For assembly to take longer. If assembly takes longer, tuning takes longer. If tuning takes longer, what type of number are we talking about? A negative number, right? If tuning takes longer, that's a negative number. So where are the negative numbers? The negative numbers are anywhere below 0. Because if I go assembly minus tuning, and tuning takes longer, it has to be a negative number. Where are the negative numbers? Below 0. So 0 is going to be that line cut there. Okay. So let's find z-scores. 0 minus 9.5 over 5.277. Negative 1.80. Go to your tables. It's going to be pretty small. 0.0 something.
It's 0.0359. There is a 0.0359 probability of tuning taking longer than assembly. Not a very good chance, because on average they take 9 minutes more, 9.5 minutes more. So there is a chance, but it's not a very big chance. Just like there's not a very big chance that they'll have the bike ready within 30 minutes or less. Okay? All right, so tomorrow I'm going to give you some time to work on the assignment. I'll have the assignment ready for you guys, and then I'll let you guys work on that. Okay?